Okay, so some of these terms should sound familiar. We, we did, ooh, we did a lot of this in grade 11, but maybe just surface. Okay, so we're just gonna go a little bit deeper now. So two main categories, the two main categories of bonds are intra and intermolecular. So intramolecular is between atoms, and if you like tricks to remember, intra has an A and atoms has an A. These forces are broken during chemical changes, so they are a little bit stronger. And on the next slide, it'll review the three main types. And then intermolecular are forces between molecules. And we talked about last year that molecule is a word that you should only use for covalent or non-metal compounds. Like molecular, molecules, okay? So these forces are broken during physical changes. So if you boil water, it takes 40.7 kilojoules. If you try to break the oxygen-hydrogen bond, it takes 934. So a significant amount of energy. Not that you need to memorize the exact kilojoules, but we're going to talk about really sort of three things. What kind of atoms, what's happening in the bond, transferring, sharing, etc., and are they strong or not, okay? So the stronger a force, so you can decide between intra and inter, or even we talked about the three types of inter, the main ones, hydrogen, dipole, and London. Which ones were stronger? Okay, we did that in grade 11. So this is going to be important for here, but it will also be important later when we talk in organic chemistry. And this makes sense. If you have a stronger force, the more energy it needs to break. You need to break it. Okay, so intramolecular forces, again, they are between atoms. So intramolecular can be molecules or ionic compounds, polyatomic ions. We talked about metallic bonds, like the weird ones with transition metals. And they, again, broken during chemical changes, so they are going to influence the chemical properties of a substance. Okay, so the first kind are ionic. And we spent tons of time last year talking about ionic. So they are a force of attraction, or the bond is a force of attraction. So opposite is very attractive in chemistry. So you can think of it like a positive and negative, cation or anion, or metal and non-metal is often what we would say as well. Now, that was probably a grade 10 thing for sure. In grade 11, there is a positive polyatomic ion that's common, ammonium. So cation and anion maybe is a better, more applicable definition. And the reason this is categorized as an ionic bond is because of the difference in electronegativity, right, which we spent lots of time doing in grade 11. So metals are on the left-hand side of the periodic table. They have a low electronegativity or electron greediness because they tend to lose electrons. And then nonmetals are very high because they tend to gain. Okay, and then we did covalent. And this is sharing with nonmetals. So ionic compounds with their plus minus, plus minus, plus minus. That's very rigid and ordered. So why would some atoms share? Well, it's not quite the same type of bond as ionic, obviously, but it still occurs where to make the molecule more stable. So if atoms were more stable by themselves, then there would be no compounds, but there are millions, right? So creating a bond makes the system more stable, which means less energy. It provides a balance with the force of attraction and the force of repulsion. So we just looked at trying to draw it symmetrical. We're going to do 3D shapes and how we deal with repulsion from electrons that are already paired up versus bonds. So you'll look at how, or we will look at how even when it's shared, it still produces a characteristic structure. It's not plus minus, plus minus, plus minus, but it definitely still wants to keep the surrounding atoms as far apart as possible, while still being able to attract electrons to the nuclei. So we just talked about this. It can result in a noble gas configuration, like the stable octet, but as you know now, it doesn't have to. Okay? And then the last type was metallic. So with transition metals. So transition metals have a very strange electronic structure. And we're going to talk about the properties of solids. That's the second part of this tomorrow. So we'll look a little bit more at metallic solids. They definitely do not conform to Bohr's rigid, flat 2D shapes or 2D orbitals. So hopefully your previous teachers really have got you to skip the transition metals because they have such a strange electronic structure. So if something doesn't have a specific spot, we call it delocalized. So they have delocalized, mobile valence electrons, which means they can move around, which then that means that they can bond with other metals that are similar. So like brass and bronze is a mixture of transition metals. It means that transition metals on their own are able to conduct electricity and heat. We use copper wiring in our homes in Canada. So if they didn't have that property, then we wouldn't be able to do that. Maybe you have copper pots in your house. Some people prefer to cook with them, because of the conduction of the heat. Okay? So intramolecular forces, metallic bonding is pretty cool. So we're going to do the second section to this is all about weird solids, okay? And then ionic bonding, we sort of exhausted what we want to do with it. So what we'll do is we're going to focus more on the intermolecular forces. Okay? So again, why molecules, why covalent compounds? Well, once you start to share, then sharing can be unique, right? I split a cookie in half and I say, here's half for you, here's half for somebody else. Who do I give the big half to, right? Sharing does not have to be equal or fair. Some atoms are very greedy for electrons and some just aren't. So last year, actually, we drew a diagram and it was like a flow chart. So once you did the subtracting and you decided it was ionic, then that was it. We didn't draw any intermolecular forces. And then if it was nonpolar, you picked one. And if it was polar, you picked one. Or you could pick from two. Then you had to look for a hydrogen, that kind of thing. So we're gonna talk about them a little bit more in depth. So dipole is kind of a general category for polar molecules, but then strange things can happen. So ion dipole, we kind of talked about this when we looked at water solubility, or if something dissolves in water, but I didn't call it ion dipole. So you actually already drew this picture. Induced dipole, so you actually talk about this in grade 9 in electricity. When you hold something that has a charge close to something else, you induce a charge in that something else. And then London dispersion and hydrogen bonding we talked about in grade 11. Okay? So London dispersion is the weakest intermolecular force. And here's where we sort of kept it simple last year. So last year if it was nonpolar, then all you chose was London dispersion, right? So London dispersion is in everything, but it's only found, or the only force found, in nonpolar, okay? And noble gas. So last year we would have just focused on the nonpolar part of it. And some of you now will have taken biology and you talk about how there are many molecules that actually can be a bit of both, nonpolar and polar. So what's going on there? So it's not as simple as we just kind of scratch the surface in grade 11, but that's okay. So we're going to, instead of only using this chart to help us decide what kind of intermolecular force, we're going to look at a different way. You can do this as well, okay? A different way you can compare the forces. So I think these points are literally from my grade 11 note. Electrons are always moving and always vibrating. That's a key component to matter. So what happens if you have something nonpolar, which is equal sharing, in case you need a reminder. So equal sharing, well, that implies no slightly positive, no slightly negative. What's going on? So there can be a magnet, or maybe the spin is just weird all of a sudden. Maybe the electrons vibrate to one side of the molecule versus another. And what happens then is momentarily, so it says instantaneously, has to be nearby, momentary attraction. These are not super strong forces. So if I'm a molecule and something's happened to me and I turned slightly negative here, then if I go by molecule Abby, I'm going to influence her to change her dispersion. Slightly negative, she'll become slightly positive. Slightly negative, then she'll influence molecule Callie, slightly positive, and so on and so forth. If I move away, Abby will go back to what she normally was, same with Callie, and it all falls apart, okay? So they have to be close together. It's only for a moment or instantaneous, but there's not just 3 molecules in a vessel, right? So then it just sort of influences all the way through the container. You can't do this with gases because they're too far apart and too fast. Okay, so momentary uneven charge distribution in nonpolar molecules, or the nonpolar parts of a molecule, because it can sort of be a bunch of them. For us in this class, we don't need to consider both necessarily, but especially in biology, because you'll talk about like hydrophobic and hydrophilic, like what's attracted to water and what's not. So considering both like different kinds of situations will be a little bit more important. Okay, so how do we decide, or how is the strength changed? Then you have to look at the number of electrons. And the straightness. Okay, so when we look at our example, then we're going to literally count the number of electrons and compare them to see the strength of a London dispersion force. The straightness of the molecule has more to do more with like biology and organic chemistry and atoms like carbon. But this can really be done with anything. So this can be done with organic ones, but this is usually saved more for that. So all you have to do is count. So how many, similar to what we did this morning, nitrogen versus oxygen or whatever, how many electrons are in a molecule? So if you have a larger molecule, then it's basically like more spots for a dispersion force to form. If you have stronger forces, more energy needed to get them apart. If a molecule is straighter, then that means they can lie together better, and again, more spots for dispersion forces to form, and they're going to be stronger. So one of the examples you can use here that you guys know about is methane and gasoline. So in gasoline, gasoline is a very, very unpure substance, but we'll consider octane. So I know that you haven't done organic yet, but how many carbons do you think are in octane? Pardon? I heard someone say it, I thought. In octane? Yes. Good. Okay, I'm not going to draw the hydrogens in because they'll get in the way, and they're just fillers. So if you have methane, which is the gas that comes out of our gas taps, then you can have one carbon and let's say one spot for dispersion. If we have octane, how many spots? 8. Okay? It's unfortunate that we use the word gasoline for this, but really, when you pump octane into your car, what state is it? Solid, liquid, or gas? Liquid. The gas that comes out of our gas jets back there is a gas. And the reason is this has hardly any force holding it together. It can get far apart, gas. This has all of these spots to make dispersion forces, tighter force, stronger force, liquid. So imagine in the back, how do we light a Bunsen burner? How do we ignite methane gas? What do we use? Yeah, a spark. So imagine you're driving your car around, friction, spark, whatever, and if it was a gas, your car could explode. So liquid is a little bit less reactive. So we're not as worried about our gas tanks igniting, right? So this has huge implications for what we do. And the same thing here. Imagine if we had, there's all kinds of reasons. Like if you had a bowl of gasoline and we ignited it and then we had to use that, what? That would be creepy. A bowl of fire, so gas, we can control it. It comes out of the gas nozzle, it goes through the hose, comes out of our Bunsen burner in this nice little hole, easy to ignite. So we exploit this a lot as humans too. This, if you're a health nut, you may have read about saturated and unsaturated fats. So saturated fats mean they are straight, which means they stick together, and they are fats. So literally inside your arteries is a fat, is clogs. Unsaturated fats have double bonds, which makes them not straight or kinky. So then there's a bend in the molecule, which makes them a liquid. So inside your arteries, it's oily and not a solid fat. Okay, so that has huge implications again for us. That's just one example. So this definitely is more to the organic side and the chemistry of carbon. This can be for anything. So our example is Br2 and I like iodine and chlorine. So all we're going to do is count the number of electrons. Okay? This is a little bit more, you would really have to know your example. This is a little harder to do. Okay, so again, I feel like I took this picture right out of our grade 11 note. When you have a polar molecule, so you would have done the change in electronegativity. Hydrogen is 2.2. Chlorine is 3.16. And then you would have said, okay, that means that chlorine is slightly negative, hydrogen is slightly positive, and then opposites attract. So this is a little bit more straightforward because it really sort of follows the chemistry adage, right, that opposites attract. Okay, so as soon as you have a greater attraction, more energy is required to separate them. And as cheesy as this analogy is, if you are attracted to somebody, you want to spend all your time with them, it is harder to get you apart, okay? It works, even though it's cheesy. So this one, we're going to call it in the middle, which we did in grade 11. Weakest was London, middle was dipole, and strongest was hydrogen. And then you can do sort of a similar thing. It says similar molecular weight. That's kind of the same idea as comparing the number of electrons. Okay, so when molecules are close together, so they still have to be close together for this to be important, then the dipoles will try to maximize the slightly positive and slightly negative. That makes sense, opposites attract. Then rapidly becomes weaker as they get far apart. So if you boil something, for example, then, and this point will help us do our example. The more polar a molecule, the stronger the dipole-dipole force. So, I guess it's already bolded. This can be tricky, and again, depending on what you're doing, then your teacher or whatever might expect or want you to just use trends and be able to look and see where the atoms are. What is it going to be, more polar or not? But one thing you can do here, no matter what, you can always go back to doing this. So if you have the change in electronegativity, and I'll always give you this version of the periodic table, then if it's closer to the higher end of the polar scale, then you can call that more polar than something else. So if you like something that's not super subjective, then if you do the change in electronegativity, if it's closer or higher, closer to 1.69, then you can consider that more polar. And that means the force is going to be stronger. MP and BP stand for melting point and boiling point. So those are just changes of state, and those are characteristic values. Like you should be able, they're reference values, you should be able to look them up for a particular molecule or compound or atom or whatever. Okay, so if you want to remind yourself what it means, melting point is solid to liquid, like melting, right? And then liquid to gas is melting or is boiling. And we just use these as indicators for strength of forces. The higher the melting point, or boiling point, then the more energy it needs to get something apart. So again, trying to give a numerical value. Instead of just saying high or a lot of energy is needed to get apart, how do we know that? Okay, it has a high melting and boiling point, which would be a number. Okay? So this ion dipole force, this is like when you dissolve an ionic compound in water. Oh, it says that. Ionic compounds dissolving in water. So that's what we did with this last year. And it's still following the same basic chemistry principle. So if it's negative, the anion, it's going to be attracted to the positive end. If it's positive, then it's going to be attracted to the negative end. So the example we drew last year was this. And what ionic compound do we always use? Sodium chloride. Okay? We just didn't call it ion dipole force. We talked about how if something is soluble, that means the water molecules surround the ions. We called that hydration. We did a lot more of this with like the solutions unit than the forces part. It's not the ghost of the chemistry class, it's just okay. And then the last one, this one is, again, for 100% you did not use this word in grade 9, but you can induce electric charge. So you probably had to rub a comb with rabbit fur. Remember doing that? Gross, right? So you're inducing electric charge on another object. And so in grade 9, you would have looked at like plastic and all kinds of things and how they affected with the electrostatic series. we're just going to do this super, super general, okay? An ion, like a plus or a minus, can induce the charge, or if something is already polar, okay? So again, this is really, really weak. So basically, we're going to talk about it on the slide and never again, okay? So momentarily polarized, they have to be close together, okay? So you can see how this can be limited. Okay, so the example, which like I told you guys, I filled it in by accident. This is the one this would be the question, okay? And on the worksheet, we're gonna do both in this. I tried to keep it separate. Either do the change in electronegativity or count the number of electrons, but not both together, okay? So we're gonna consider bromine and iodine monochloride. So I actually I think on the rest of the slide, I tried to use a capital L. Chlorine is very annoying. So if you wanna make this a capital L, because it kind of looks like ICI, right? That's nasty. Okay, so there are different ways you could be asked this question. It's giving you bromine's, what's it called? Boiling point is 59 and iodine monochloride is 97. So that means that iodine monochloride has a higher boiling point. So if it has a higher boiling point, are its forces stronger? Yes. But how do you know that? Let's do some definitive math so that we know. Okay? You're not guessing. Nobody wants to guess, right? It doesn't really matter what you do first. And like I said, I'm not going to make you do both. So I'm going to do London dispersion first. But the question on the worksheet says, using the number of electrons, state which molecule has stronger dispersion forces. So I've only asked you to do one type. And then other questions say, determine which molecule has stronger dipole force. This is putting them both together, okay? So we're going to do the London dispersion force, and all you have to do is count the number of electrons. So bromine has 70. How do I find the number of electrons? Where did I get the 70? Okay, so 35 plus 35. This is the atomic number. That's all you have to do. So since there are two bromines, you do 35 plus 35, which is 70. Iodine is 53. So all of these are atomic numbers. Chlorine is 17. Add them together, you get 70. Okay? So, same number of electrons means equal dispersion forces. If this was just Br and it was 35 and 70, then whichever one had the higher electrons would be the stronger force. Okay, so this is like number 7. This is all you would have to do, okay? But we're going to do the dipole as well, But again, one more time, I've split it apart, okay? This is putting it together. You don't have to do it together, okay? So then to determine if dipole-dipole forces are present, you can calculate the change in electronegativity. Now, maybe you remember that diatomic molecules are nonpolar. There are definitely trends that you can use here, okay? So, you know, don't push out of your brain things you already know, okay? Because you definitely would know that. But if you want a way to do this, to do it numerically every single time, then you just subtract. Do you need to remember what's on this periodic table? Memorize it? Never, okay? So you can use this every single time. It doesn't matter if you do iodine minus chlorine or chlorine minus iodine, whatever, okay? Once you do the subtracting, then it's obvious. Okay, this one's only nonpolar, it doesn't have any dipole. This one is polar, it's got dipole. So it has the higher boiling point because of the dipole forces. So London, that's why in the note it says, like in little writing, London is weakest, then dipole. You don't need to go farther. You don't need to say induced dipole, none of that. We're just going to do London, dipole, that's it. Okay, and then the strongest is hydrogen. The reason you don't need to worry about anything else with hydrogen is because it's very, very, very particular and very obvious. You need to have hydrogen and oxygen, nitrogen, or fluorine. So in grade 11, I tell you that you can say like FON or NOF, okay? It is very, very particular because oxygen, nitrogen, and fluorine are very electronegative. So the bond is very polar. And they're able to get really close together because the atom is so small. So anytime you have something that's close, you're going to be able to be attracted more. And that's, again, chemists love opposites attracting. Okay, so this is, again, another picture with oxygen. And this is actually what we're going to do when we do the 3D shapes. These are the lone pair of electrons. We call them, we try to use these paddles. They look like little paddles. To try to show the cloud of density of electron density from a lone pair. It pushes or repels the atoms away from it. So this is, somebody asked me about the shape this morning. This is really what it should look like. Lone pairs at the top and atoms at the bottom. So that's what we're going to do next, okay? So fluorine, oxygen, and nitrogen are very electron greedy. So then the resulting partial charge difference makes the water molecule, for example, or HF or ammonia NH3, they can easily attract something else. So actually, I think this was an assignment you could have chosen, okay, where you drew this graph. And so water and methane essentially have the same molecular weight. Water boils or changes from a liquid to gas at 100. Methane boils at negative 159. So we're so used to thinking of boiling as hot, this makes no sense. But it has to do with this one has hydrogen bonding, and this one is just dispersion.